In this video, I want to take a look at how do we use Laplace transforms to solve a second-order differential equation with initial conditions. So here we go. Here's my equation, y double prime minus 4y prime plus 4y equals e to the 2t with initial conditions y of 0 equals 1 and y prime of 0 equals 3. This is one that we could already do. This is a second order linear with constant coefficients, right? That we have a method of doing it. In fact, it's the characteristic equation would be r squared minus 4r plus 4, which factors into an r minus 2 squared. So I know that I've got e to the 2t and te to the 2t as the two solutions to the homogeneous equation, and then I would have to go for a particular equation, a particular solution, with the e to the 2t there being already part of the homogeneous and t to the 2t also being part of the homogeneous, I'd have to guess t squared e to the 2t, a times t squared e to the 2t. So in order to get the initial conditions satisfied, I would need to be able to solve for C1 and C2 from the homogeneous part and that a from the method of variation, not variation of parameters, the other one, undetermined coefficients, right? There's three variables here that I need to solve for in order to get this to work. So I got an idea what the solution looks like. It's not a hard process to solve it the normal way, and it's not necessarily a short process either. But here's a different way, and this is a way that will work in more situations than just ones we already know how to do. So I'm going to take the Laplace transform on both sides. Okay, and because the Laplace transform is a linear operator, it distributes over this addition here. So I get the Laplace transform of y double prime. It also commutes with scalar multiplication, so those constants being multiplied can come out front. Minus 4 times the Laplace transform of y prime plus 4 times the Laplace transform of y equals the Laplace transform of e to the 2d. Now, we had in a previous video the relationship between the Laplace transform of the derivatives of y and the Laplace transform of y itself. So in particular, the Laplace transform of the second derivative of y is s squared times the Laplace transform of y minus s times y evaluated at 0 minus y prime of 0. And then minus, I'm on this one now, minus 4 times the Laplace transform of y, and the Laplace transform of y is Laplace transform of y prime is s times the Laplace transform of y minus y evaluated at 0. And then I have the plus 4 Laplace transform of y. The Laplace transform of e to the 2t, you could actually do the integral, or you could look at the table. I happen to have down below the table here, and the Laplace transform of e to the 2t would be 1 over s minus 2. So I'm okay with you looking up those things for the most part. You should know how to calculate some of the basic ones like that one, but you don't have to do it every time. So anyway, there's the Laplace transform of e to the 2t being 1 over s minus 2. So what I have now is a linear equation in the Laplace transform of y. And this is what's remarkable about not just Laplace transform, but the other types of integral transforms as well, is that you take one type of problem, a differential equation, and you turn it into another one. This is now solve a linear equation. I can solve linear equations. That's good. I'm going to distribute the minus 4 through here and then gather up all the, so what's my next step? So I distributed the 4 through. I also plugged in some things I know, right? I know what y evaluated at 0 is. That's one of my initial conditions. It's 1. I know what y prime evaluated at 0 is. That's another initial condition. It's 3. So I've got this equation, which I'm now going, I'm down to here at this point. I'm going to solve for L of y. So the terms that have the Laplace transform of y, I'm gathering them up and factoring out the Laplace transform of y. So I see an s squared, I see a minus 4s here, and I see a 4 there. So there's all those terms. Everything that doesn't have a Laplace transform of y, I'm moving over to the other side. So this negative s goes over as a plus s. there's a -3 and a +4, which is a total of +1 on this side. So when I subtract it over, it's a -1 on that side. The 1 over s minus 2 is already over there. And then I can divide by this stuff in order to get the Laplace transform of y equals this big old fraction. Now, one difference I want to point out in the way I notate this and the way the book notates this is that I just keep writing Laplace transform of y. The book writes it as capital Y of s. So then quite often it gets shortened to capital Y. And I don't do that because I've seen too many times students forget what they're doing. That they get to this point and they have capital Y equals this. And they say, I'm done, I've got Y. It's like, well, you weren't looking for capital Y, you're actually looking for little y, right? The original y was a lowercase y, and now you got a capital Y anyway. So I specifically leave it as Laplace transform of y, so I know how to get out of it. I know how to get to y itself. I've got to do an inverse Laplace transform. So, at this stage right here, I'm going to simplify matters. Essentially, I'm going to multiply top and bottom of this fraction by s minus 2. So that fraction times s minus 2 is just this one. The s minus 1 times s minus 2 looks like that, and then I've got this on the denominator. Now, I also happen to notice that s squared minus 4s plus 4 factors into s minus 2 times s minus 2, and so I end up with an s minus 2 cubed on the top, and in the numerator I've just multiplied this out, so s squared minus 3s plus 2, but then there's another plus 1, so it's plus 3 there. Now, all I need to do is take the inverse Laplace transform, except that this doesn't look like anything on the list. There is some stuff in the chart that's got this s minus a to the n power, but it has only a number on the top, n factorial. So I was thinking I could just distribute this divided into that and into that and into that. So I could probably handle the 3 over this thing, but I don't know what I'd do with those other 2. So instead what I'm going to do is I'm going to do, where am I? I'm right here at this point. I'm going to do partial fraction decomposition. Okay? And this is the same as the way we do it in Calc 2. When you've got a linear factor raised to a power in the denominator, I'm going to write it there to the first power, to the second power, to the third power. I keep going up until the power that I have total, and that's to the third power. Okay. Again, I always seem to forget to mention that, hey, the power in the numerator is 2, the power in the denominator is 3, so partial fraction decomposition should work. And with this linear denominator, I can go with a constant numerator on each of those. Right? It's not like these are unfactorable quadratics, which force me to a linear numerator. This is just all the same linear factor, just raised to different powers. If I now multiply both sides by that denominator right there, then the left-hand side is this, and the right-hand side, in this case, one of the s minus 2's would cancel out, leaving a times s minus 2 squared, and this one, 2 of the s minus 2's would cancel out, leaving a b times s minus 2, and on this one, all 3 of them cancel out, leaving just the plus c. Okay. And so I'm going to solve this by plugging some numbers in. I got to solve for a, b, and c. So if I plug in s equals 2, the right-hand side is 2 minus 6 plus 3. And the right-hand side, there's a 0 right there and a 0 right there. You just get a c on the right-hand side. And so c is equal to 1. Plugging in a 0 for s, the right-hand side nicely just becomes 3. This is a negative 2 squared, which is 4. So I've got a 4a. And then I've got a negative 2 times b, which would be negative 2b. And then I've got a plus c, but c I already know is 1, so I'm putting the 1 right there. When I bring that over to the other side, that makes that a 2, and I happen to notice that everything is even, so I've divided everything by 2. So this 2 becomes the 1, that 4 becomes a 2, and the negative 2 there becomes a 1, or negative 1, right? So anyway, that's two equations. Sorry, that's an equation with two variables in it, a and b. I need another equation, so let me plug one more value of s in. So I'm plugging in 1. So I got 1 minus 3 plus 3 over here, and the 1 minus 2 is -1, which is kind of nice. When I square it, I get 1. So that's just an a. And then right here, this is a negative b, and then plus c, but c I already know is 1, so I have that. So a minus b is equal to 0 when you get this one together with that stuff over there. A minus b is 0. So I got those two equations that I want to solve for a and b. If I subtract the equations, top one minus the bottom one, on the left-hand side I just get an a, and on the right-hand side I get a 1. So I know that a equals 1. I can plug that into there and see that b also has to equal 1. So that was rather nice that a, b, and c are all equal to 1. So the Laplace transform that I'm looking for could be rewritten this way as the sum of these three fractions. And then the Laplace transform, sorry, the inverse Laplace transform is a linear operator. It distributes over addition, and so I get that. Now looking at this chart, I can see the 1 over s minus 2 would be right here with a equal to 2. So that's going to be the e to the 2t. This one right here is looking like this one, because I've got the s minus 2 to the 2 power. So that would have n equal to 1, right? Because this is written as n plus 1, so the 2 sitting right there is a 1 plus 1, which means I need a 1 factorial on the top, which is what I have. Okay, so that's a 1 factorial on the top. And so this is going to be, so n was 1, right? There's a 2 there. That was an n plus 1. So n was 1 in this case. So I'm going to have a t to the 1 times e to the whatever's in there. It's 2, e to the 2t. So this is going to be t e to the 2t. And this last one is again looking like this one. However, with a 3 here, this is saying that n is 2, so I need a 2 factorial on the top. I have a 1 on the top. 2 factorial is 2, so if I were to change that 1 into a 2 times a half, then I could factor out the half. So down below here, that's what I've done. Here's the 2 times a half, and now I can say this one, the inverse Laplace transform was this, was e to the 2t. The inverse Laplace transform of that was t e to the 2t. And the inverse Laplace transform of this is, right, with this n equals 3 in here, so actually n equals 2, so it's 3 plus 1, then this should be a t squared e to the 2t. That's what I have there, and the half had come out so that I could make that a 2, and so the half is still up front. This is the form that I was expecting for the answer, and so it's nice that it is. Here I found that both of the coefficients that I would have gotten from the homogeneous equation are 1, and the coefficient that I would have gotten in the undetermined coefficients was a half. Now, I was going to do 2 examples in this video, but as you can see, that one already took 13.5 minutes, and the next example I want to do is even bigger. So we'll save that for the next video.